Okay, welcome back. For the second talk of the morning, we're happy to have Chi-Ming Chang for Tsinghua University, who will tell us about Fortuity and SYK models. Please, let's welcome Chi-Ming.
Okay, I would first like to thank the organizer for a kind invitation. I'm very happy to be here to share with you our recent results. And in this talk, I will talk about my paper from last December with Chi-Ming Chang, Bisung Xie, and Yang Zhenbin. Okay. So we all know that research in holography has uncovered many remarkable quantum properties of black holes, such as maximal chaos, page curve, and the random matrix behaviors. And so in this talk, I will introduce a new property, and it's called Fortuity. And this property is for the supersymmetric or BPS black holes. Very roughly speaking, Fortuity, this property can be used to distinguish the microstates of black holes from the microstates of horizonless geometries. And the way to distinguish them is by trying to relating the BPS states or equivalently the Q-cohomology classes in the dual theory of different rank N. So let me come to more detail. And so this is the outline of my talk. I will first give a brief introduction to the supercharged Q cohomology and this new property Fortuity. And then I will focus on the model Angus-2 SYK model, and then discuss that a very interesting relation between the property Fortuity and another property that's called R-charge concentration. And then I will discuss this R-charge concentration in a slightly slightly generalized SYK model that's called the two-flavor SYK model. And also, so we will learn some lessons from the R-charge concentration in the two-flavor SYK model, and then we can apply that lesson to the case of Angus-4 super Young mills, and that can tell us some new thing. And then I will discuss the relation between Fortuity to some other signature of black hole, such as chaos, randomness, and entanglement. So first about the Q cohomology, and we can consider a very general setup. Just consider a quantum system with a complex supercharged Q and its complex conjugate Q dagger, and they satisfy the supersymmetry algebra, the anti-commutator of Q and Q dagger, that in the supersymmetric quantum mechanics that just give us a Hamiltonian. But now we consider a slightly more general framework and include also supersymmetric QFTs. So the right-hand side will be Hamiltonian and with some shift. And this shift, I call it EBPS, and that's completely determined by the charge or angular momentum. And we can just work in a sector with a fixed charge and angular momentum. So this EBPS will be a fixed number. And the supercharged Q and its Hermitian conjugate, they are both nilpotent. So Q square equals 0 and Q dagger square also equals 0. A very straightforward consequence from this supersymmetry algebra is that we have a lower bound for the energy of the states. So that's the BPS bound. And in this talk, I will focus on the states that saturate this BPS bound, and they are called BPS states. So they have energy exactly equal to EBPS. And these states, you can describe them in a different way, that they are states annihilated by both supercharged Q and its Hermitian conjugate Q dagger. And there's a very nice tool to study this BPS state is from this one-to-one correspondence between BPS states and the Q cohomology classes. So this Q cohomology is defined by consider the space of all Q closed states and model the space of Q exact states. And this one-to-one correspondence tells us that given a Q closed state, we can always find some Q exact state and add to it such that the resulting state is also annihilated by Q dagger, and that's BPS. And we are interested in studying the supercharged cohomology in holographic theory. And so we also want to introduce some ingredients in holographic theories. So in holographic theories, usually we have this type of quotient structure. So we consider the Hilbert space of some rank n holographic theory. So the holographic theories are labeled by the rank. So it's when we talk about holography, we are not just focusing on a single theory, but a sequence of theory, and they are labeled by rank n, and consider the Hilbert space of that finite n theory. And this finite Hilbert space in most of the holographic theory can be realized as a quotient. So this H infinity, that's the infinite rank Hilbert space. So we consider the infinite n theory and its Hilbert space formally denoted by H infinity. And the finite n space that's given by the infinite n space and quotient out by some equivalence relations. And so in different type of holographic theories, we have different kinds of equivalence relations. For example, in N=4 super Young Mills, the equivalence relation would just be trace relations. So if we consider the multi-trace operators, and the multi-trace form of the operator is ambiguous because there can be some relation between different multi-trace and different multi-trace form actually describe the same operator. So later on, I will talk about SYK model, N=2 SYK model, and in that case, I will also introduce what's the equivalence relation we talk about. Yeah, if you have so the equivalence relation at larger n will always be equivalence relation at lower n. So later on, I will tell you more about that. Yeah, some filtration structure like that. Okay. That's right. Yes. 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 So here actually, I need to only consider the vector space. So even though I talk about Hilbert space, I only keep the vector space structure. I do not talk about the norm, because the norm can depend on coupling, and you cannot quite relate the norm of the finite and infinite space. Oh yeah, if you introduce the norm, yeah, that's right. The relations will have zero norm. Yeah, then they are quotient out at finite. Yes. No. So, if you introduce a norm, and then so the relations will have zero norm, but the non-relation will always have finite. So have some positive norm. Okay, good. Okay, so finally, because I've introduced two structures. First is supersymmetry structure, and the other is this quotient structure. And we want these two structures to be compatible because I want to use them all. So I need to impose a condition that Q and pi commute. So this pi is the quotient map. Good. So now let me try to use the above two structures. And let's start with a Q cohomology class, and I denote it by psi. That is represented by a Q closed state. I also call it psi, that in the finite n Hilbert space. And now I can use this pi map to lift this finite n state psi to a state I call it psi tilde in the infinite n Hilbert space. That means if I act pi on psi tilde, that give back psi. And now I want to use the the compatibility condition. So we know that by our definition, psi is Q close. So Q act on psi give us 0. And we also know that psi is given by pi psi tilde. So we have this formula. And then I use the fact that Q and pi commute. So I get pi act on Q and on psi tilde. And so we know that Q psi tilde, that's annihilated by pi. And saying in other words, it should be a relation at this particular n. So Q acting on psi tilde is inside In this space. And now we want to find solutions to this condition. And there are two possibilities, two solutions. The first case I call the resulting, the cohomology class, I call them monotone class. The definition is that if there exists a lift psi tilde such that this state is actually just 0, is a trivial relation, is just equals 0. And actually, because we have, so I will not tell you detail, but because we have pi q equals 0, so this state psi tilde actually is not exact. So it's close but not exact, and that gives us a cohomology class psi tilde, non-trivial cohomology class. And another possibility is that you cannot find a lift such that Q psi tilde is trivial, is 0. So you always get some non-trivial element, a non-trivial relation. Okay. Good. So these are the two definitions for monotone class and fortuitous class. So now let's try to explore the consequence, the properties of monotone and fortuitous classes. So first about the monotone class. And we want to study holographic theory, so we want to consider larger limits. And to talk about larger limit, let me add a subscript n to this projection map pi. So that I can talk about projection to different finite rank theory. So this pi with rank with subscript n means this particular projection I project to the rank n Hilbert space. And now I can consider the higher projection that projects to project this psi tilde map to rank n plus 1, rank n plus 2, and so on, these higher rank theories. And now the question I would like to ask is that whether this sequence of states give us Q cohomologies and hence by the one-to-one correspondence give us BPS states. So first, let's explore the case of monotone. And so to check whether they give us Q cohomologies, let's check that whether we get Q closed states. So I add Q on this sequence of states. And now I can use this compatibility condition, Q and pi commute again, and that gives us pi Q psi tilde. And because the last state is monotone by our assumption, so Q psi tilde is 0, and that gives us 0. So indeed, we get a sequence of Q closed states. And this compatibility condition, Q pi commute, will actually also tell us that this sequence cannot be Q exact. So we actually get a sequence of Q cohomology. And then we use the one-to-one correspondence between cohomology classes and BPS states that give us a sequence of BPS states. And so this property is kind of summarized by this diagram. So we have a sequence of states, their energy are all eBPS. And now let's consider the second situation, the fortuitous case. Again, we look at this sequence, but now the situation become more complicated, because these state, I mean, Q acting on psi tilde is non-trivial. It lives inside the space of relation, is a non-trivial relation. So I need to introduce a bit more about the properties of these relations. So the first property of relation is that we get fewer relation at larger n. So a relation at rank n plus 1 is always a relation at rank n. And from the example of Engel's 4 super Young mills about this trace relation, it's kind of obvious because we can always embed a smaller matrix into a larger matrix. So if a larger matrix satisfies certain trace relation, then of course the smaller matrix will also satisfy that relation. And there's a second property that I will use is that there are no relations at infinite n. And from the trace relation example, it's also quite clear that in the infinite n case, all kinds of multi-trace formula you can write down, there will be no ambiguity. They all represent independent operators. And this condition, more detailedly, is actually this more precise statement that there is a critical there's a critical I call it NC, and such that if I consider n smaller than nc, then this state is a relation. But when n greater than nc, q psi tilde is not a relation. It's something non-trivial. So this means that I have the following situation. There's a finite sequence of states. They are actually Q close because Q psi tilde is a relation. But if you increase n beyond this critical NC, the state is not Q close. So I get a finite sequence of Q cohomology, and also by the correspondence, I get a finite sequence of BPS states when n below NC. But if I consider n greater than NC, these states, they are not Q close and also not BPS. So I get this situation. In the particular example, I mean, okay, in Engel's 4 super Young mills, we have construction for explicit fortuitous state or operators, and in that case, you can consider the eigenvalue, so the eigenvalue you can actually in that case that would be actually a function of n, and you can actually change n continuously, and in that case you can really see that they have zero. Sorry, the energy is exactly equal to EBPS at in that case n equals 2. But if I increase energy, you can see that n really, I mean the energy really. So if you increase n, you will really see that the energy really increase. So it might not end at n equals 2. That's because the state psi itself can become the relation if you go smaller. Yeah. Before, yes, that's right. Before n equals 2. Yes. Right. Good. Okay. So now we've seen these two very distinct properties for monotone and fortuitous states, and using this property, we propose certain conjectures for their bulk dual. So first, for the monotone states, our proposal is that they are due to the microstates of horizonless geometries, and but for fortuitous states, the proposal is that they are due to microstate of black holes. And there are some evidence for these conjectures. For example, in the case of Engel's 4 super Young mills, on the box side, there are certain smooth horizonless geometry. They are called Lin-Rooney-Malasena geometries and their generalizations. And these geometries, they are all due to monotone states in Engel's 4 super Young mills. And in the case of D1, D5 CFT, there are also smoother horizonless geometries that people have found. They are called superstrata geometries, and they are also due to monotone states in the D1, D5. But in this talk, I will not talk about the Engel's 4 super Young mills or D1, D5 CFT. So I would not tell you more about this. But here I have actually a very intuitive argument for the underlying reason why we would like to propose that conjecture. So because we want to have some bulk dual that match with these two pictures. So first, let's consider the case of horizonless geometry. So for these two pictures, we are interested in the larger limit of the sequence. And the larger limit on the box side correspond to the G Newton go to zero limits. So we want to consider some box solution and then try to take the G Newton to zero limit. So let's first start with the smooth and horizonless geometry. And these geometry, they have a smooth G Newton to zero limit. That's because they can be viewed as coherent states of gravitons. And if we take the G Newton to zero limit, so this solution will actually just disassembled into some non-interacting graviton gas. But on the other hand, it's actually highly unlikely for BPS horizonless geometries that becomes non-BPS as G Newton go to zero. So it's actually highly unlikely for them to be fortuitous. Because for fortuitous state, if I take larger limits, they should become non-BPS. And if you have some smooth and horizonless geometry, I could not quite imagine how this thing can happen. But on the other hand, if you consider some black hole geometry, and then again try to take G Newton to zero limits, and in this case, we can see that the solution will actually become singular. So importantly is that when I take this limit, I want to fix my energy. That is because I want to try to match with this picture, and I want to fix my energy and then take larger, and that means G Newton to zero limit. And for the black hole geometry, if I fix energy and take this limit, the geometry actually become the horizon will shrink to zero size, and the geometry become a naked singularity. So that means something must happen. And if you want to keep the horizon smooth, you actually need to increase energy, and that match with like at least qualitatively with this picture. So here I talk about a single state that I mean on the CFD side I talk about single state with this property, and so. But I mean as you said that for the black hole geometry that actually corresponds to ensemble of many states, and so I think the idea is that if the majority of the states has this property, and then the geometry should have similar property. Yeah. So part of our conjecture is that a typical black hole microstates should be fortuitous, so should have this structure. Okay. Good. And there are some other conjectures also involve monotone and fortuitous states. That's by Chandling and Schenker. So the conjecture is that the fortuitous states are strongly chaotic, and the monotone states are at most weakly chaotic. There are again some checks and evidence from the explicit computation in D1, D5 and equals force Villamils. And there's also an intuitive argument. And the argument is that we know that the non-BPS states, they are strongly chaotic in this case. And but for fortuitous states, the chaos of the non-BPS state kind of invade the fortuitous sector. So because for fortuitous states, the BPS state and this non-BPS state, they are kind of related. So that's the invasion picture they have. More explicitly, that can be you can know this by this LMRS diagnostic, and I would actually tell you more about this when we discuss the SYK model. And in SYK model, we can also try to check this conjecture to see that whether the monotone and fortuitous state they are strongly chaotic or weakly. Okay. I mean, of course, from this study of Engels-4 superyamules and D1, D5 CFT, these theories are complicated theories. And it's actually very hard to construct fortuitous classes or fortuitous states for this theory, in these theories. And the explicit constructions are all at low rank. So due to the limited data available, our understanding of fortuitous states remains very preliminary. And very natural question to ask is that whether we can find the simpler models, and then using this simpler model, we can explore more properties of fortuitous states. So that motivates us to study the Engels-2 SYK model. So let me first give some short introduction of Engels-2 SYK model. And it's a generalization of the non-supersymmetric SYK model to the case with Engels-2 supersymmetry. So it's a system of n complex fermions. I denote them by psi. And this system has a complex supercharge Q. So Q is made out of 3 psi. And so it's just this psi, Ψj, Ψk with some coupling Cij, and this supercharge satisfies the supersymmetric algebra. In this case, H just equals to QQ dagger. This EBPS in this case, because I consider SUSY quantum mechanics, EBPS equals 0. And it's also easy to see that Q and Q dagger, they are both nilpotent. So we have this algebra that this supersymmetric algebra. And I can also write down the number operator for psi, that's just psi dagger, and this would be the R charge of the system. And in most of the discussion of SYK model, this coupling Cij would be some random Gaussian variable. But for us, we would just take this Cij to be one instance of to just be a single realization, and we would just take Cij to be a very generic 3 tensor. No. That's just because I mean this is fermionic, and you just have I mean this is Grassmann, so 2 Grassmann numbers square equals 0. Yeah. Because the important thing is I do not have psi dagger in this formula. So psi square equals 0, and psi dagger any commutator gives us 1. Good. Okay. Let me before analyzing the Q cohomology in Engels-2 SYK model, let me first give some general remarks. So first, the correlation functions in Engels-2 SYK can be computed exactly at large n, and the technique to solve them is the Schwinger-Dyson equation. And in particular, we can consider the all-time order 4-point function, and that 4-point function exhibits maximal chaos. And this maximal chaos is the signature of the dual black hole. And at low temperature, the Engels-2 SYK model is dominated by Engels-2 Schwarzian sector. And this Schwarzian sector is due to Engels-2 JT supergravity in ADS2. And this Engels-2 JT supergravity also describes the near horizon excitation of BPS black holes in ADS5. Okay. So from this relation, we can also see that the Engels-2 SYK model is closely related to Engels-4 superyamules because from this Borg relation. So now let's come to the cohomology in Engels-2 SYK. by some direct computation, people have found that n equals 2 SYK has a very interesting BPS spectrum. So first, very importantly, this BPS spectrum has no ensemble fluctuation. That means as long as I pick a very generic CIJK, you get the same BPS spectrum. So that's why we actually do not really care about the specific form of CIJK. We just need a very generic one. And the spectrum has this very interesting structure. It exhibits some property we call R charge concentration. That means all the cohomology classes or BPS states, they are concentrated at near R charge roughly equals to n over 2. So the R charge previously I defined it to be just a number of psi. So it is shown by this diagram. So all the BPSA are concentrated on this red line. And because of this R charge concentration property, we know that actually all BPS states are fortuitous. So that is because let's first fix the R charge, fix n psi, and then try to increase n. And we can see that only at this intersection, we will get BPS states. And if I go above, if I increase n, go above n over 2, then these states are non-BPS. Yes, become the relation. Okay. And this property that all fortuitous actually very nicely also match with our bulk intuition, because previously, as I said, that the n equals 2 SYK at low temperature, that's completely captured by the n equals 2 Swazian, and that's related to n equals 2 JT, and that's the near horizon excitation of black hole. Okay, so they are all fortuitous. And this R charge concentration actually follows from the property that our supercharge is very generic. It follows from the genericity of supercharge. And let me try to argue this. So let me start with a vacuum state denoted by omega, and it's defined by the states that are annihilated by all psi dagger. And given these vacuum states, I can construct states by acting fermion on omega. And so it takes this form. So a state can be viewed as a P form. That's because all these fermion, they are like Grassmann fields. So these indices are fully antisymmetrized. So that this alpha is a fully antisymmetric tensor. And of course, the degree of the form equals to the fermion number. And now let's consider the supercharge action. So because supercharge, you can also view it as a 3 form. That's again followed from the fermion statistics. So the indices of C should be fully antisymmetrized. And the supercharge action in this form language is actually just given by wedging a 3 form with our P form. So given a P form, the supercharge acts, and you get C wedge P, C wedge alpha. Okay. So now let's consider. Let's try to compute the Q cohomology. So first, we can, before compute the Q cohomology, we can compute the dimension of the space at particular degree P. And the dimension of a P form, that's just given by n choose P. And so here, this diagram just schematically plot the dimension of the space of a P form. And now let's focus on the case when P less than n minus 3 over 2. That's this region. So at this region, we have that the dimension of the space of P form is less than the dimension of the space of P plus 3 form. So C increase the degree of a form by 3. And so so here, the thing I'm comparing is the space before the Q action and the dimension of the space after the Q action. And now if this 3 form is generic, then it's kind of clear that the only solution to C wedge alpha equals 0 will be that this alpha is C wedge some other lower degree form beta. So because of this, we know that there are actually no cohomology classes or no BPS states if P is less than n minus 3 over 2. So if at this region there are no any BPS states. On the other hand, we can look at the other side. So consider P is greater than n plus 3 over 2. And in this case, I can apply the similar argument. I just need to exchange psi with psi dagger because we have this charge conjugation symmetry. And again, in that case, we also do not have any BPS states when P is greater than n plus 3 over 2. So then we know that all the BPS states are actually concentrated near n over 2. But here we see that actually, I mean, this concentration is very sharp, that you actually do not get any BPS state if you are outside this region. But this can be made even sharper. This concentration can make even sharper. The reason is that so Q will actually increase the R charge by 3. So we can actually split our space into 3 distinct cochain complexes that are refined by, I mean, these 3 cochain complexes have different Z3 charge. These Z3 charge is defined by P mod 3. And so these 3 points, they actually belong to 3 distinct cochain complexes. And if you focus on a single cochain complex, then all the BPS states, they are concentrated at a single R charge. So in this case, we get actually a very sharp concentration. Mm-hmm. Yes, that's right. So for, say, you consider supercharge made out of Q fermions, and the spread will be Q. Yeah. But if you further refine that to individual cochain complexes, then there's no spreading. You can see exact concentration. So we've seen that this R charge concentration is closely related to the genericity of supercharge. And actually, we can argue that for our particular supercharge, that's the most generic 3 local supercharge of the 1D fermion system. Because the other 3 local supercharge you can try to write down would be, say, of this form. You have 2 psi and 1 psi dagger. But this coefficient D will be constrained by the nilpotency condition. And then due to this nilpotency condition, you have actually much fewer degrees of freedom in this coefficient than the previous coefficient C that we have if all the fermions, if you use 3 psi and without using psi dagger. So this form of supercharge is the most generic one. And then due to this observation, we propose the following conjecture. That is, if you consider a generic Q local complex and nilpotent supercharge in and you consider larger limit and consider near the BPS bound, then the BPS state should concentrate it at a particular R charge. I call it RC in a cochain complex. Okay. And so here in this conjecture, there's one unknown, this RC. In this conjecture, we didn't specify which value of RC that the BPS state are concentrated at. But this RC can be determined by looking at the index of the system. So from the SYK model, this n equals to SYK model, by explicit computation, we know the value of RC. But in the general case, this RC can be determined by consider the index. So let's consider a larger limit and focus on a scaling region that we consider the R charge is scaled like some constant R times n to some power. So this particular power would depend on different theory. In our previous discuss, this n equals to SYK, this power would just be 1. And in this larger limit, the degeneracy of the space, the degeneracy of the states, dr, I would assume that to scale with the same power. And this scaling, and this coefficient, that's the entropy. And now let's consider the index of the system that's just given by trace of -1 to R. And so this can be rewritten as the sum of -1 to R with, with the degeneracy of the space at a particular R charge. And now let's consider this scaling region. And because we consider larger limit, we can write this sum of R charge as this integral of small r, and then plug in this scaling formula and get this formula. And then we can, because we consider larger limit, we have a large coefficient in the exponent. We can apply the saddle point approximation to this integral and then get this formula. So this R star is the saddle point value, and it solves this equation. And now, so this would just be some standard saddle point approximation of the index. But now, if I assume that by our conjecture, the BPS states are concentrated at a particular R charge and call it RC, then the conjecture implies that the index take this formula. So that means in this sum, I only need to consider a particular RC because all the BPS states are at that particular RC. So I get this. So I have the degeneracy of the BPS subspace at that particular RC, and then time multiply this phase. Now I can compare the phases between these two formulas, and then I can read off the value of the smaller RC. That's right. So, but the point is that here this small RC is multiplied by a very big number. So this shift will be a huge shift. So this small RC, modular this huge shift is unambiguous. Good. We can, as an exercise, we can try to apply this to the n equals 2 SYK model, even though we've already know the place where the BPS states are concentrated at, but we can, as a check of this method, we can apply the method to n equals 2 SYK. And from this index analysis, we indeed can find that RC is concentrated near n over 2. Okay. So next, let us move on to consider the system with more some generalization of n equals to SYK. So the idea is that because we know that in more realistic models, the supercharge might not be, in the most model would not be fully generic. And however, we still think that it would be closely being generic if we consider the sector near Fortuity states. And so that is why we want to study some models that the supercharge will not be fully generic. And the model, and this generalization of the n equals to SYK will contain both monotone and Fortuity states. So in this case, we introduced two types of complex fermions. One we call is psi and the other call them chi. And the supercharge is made out of two psi and one chi dagger. And in this system, we have two U1 charge. And first, that is the number of psi, and second is the number of chi. And the R charge is identified as minus number of chi, because we can see that the supercharge contains one chi dagger. And besides the R charge, we can find a combination of U1 charge that commute with our supercharge Q. And in this model, we can construct some monotone states. And they take this form. We have a bunch of psi acting on the vacuum states. And it's actually easy to see that these states will be annihilated by Q. So that's because the Q contains one chi dagger. And for these states, we do not have chi excitation. So it would be annihilated by Q. And so they will be Q closed. And these states can be, by the one-to-one correspondence, they can also be promoted to Q exact, to promote to BPS states. They will be Q closed, but not Q exact. So by some explicit computation, we indeed see this spectrum. So we have some BPS states that they are fortuitous and they live near n chi equals n psi. But there are also some monotone states that they only have psi excitation and do not have chi excitation. And for fortuitous states, we see they also, they concentrate in this region. Yeah, so this is for n equals 9, and we just consider a particular, very generic, this CIJK. And again, in this case, if you consider generic CIJK, the spectrum, BPS spectrum will not change. So here, it's actually not very easy to see R charge concentration, but again, you can try to consider individual cochain complexes, because we have this U1 charge J. We can consider Q cochain complex with different value of U1 charge. And after this refinement, again, you can see exact concentration. So there's all the BPS states are concentrated at a particular value of R charge. In a larger limit, and using this index analysis, we can also find where the fortuitous states are concentrated at. So we have this diagram. So this x-axis is the number of psi, and y-axis is number of chi, and all the BPS, these fortuitous states are concentrated at this red curve. And of course, at these two edges, you can have some monotone states. So in the larger limit, due to the power, due to the simplicity of SYK model, there are lots of other tools you can use. For example, in the SYK model, in larger limit, is described by the classical equation motion of the bilocal G sigma action. And this classical equation motion is equivalent to the Swinger-Dyson equation. And this classical equation motion can actually be regarded as the analog of the Borg supergravity equation. And by solving this G sigma equation motion, we found that this red curve coincides with the location of the SYK solution. So the SYK solution to these three sigma equations, they're also located at this red curve. So this tells us some important lesson, that is the R charge concentration can actually tell us about where the SYK solution live in the solution space of the supergravity equation. Because as I said, that the equation motion for this G sigma action, that's the analog of the supergravity equation. Say if you consider the case of angle small superyamules and its dual supergravity. And we find that the SYK solution to these G sigma equations coincide with this, where Fortuity state lives. So we consider other generalization of SYK model, and in all the cases we found that the solution to G sigma equation motion coincide with where Fortuity state lives. Okay, at least for the class of SYK model, we found it true for all the system we studied. The next thing is I want to apply to angle spore. Okay, so now let's try to apply these lessons to angle spore and try to see that whether the R-tri concentration tell us about the solution space of the where the SYK solution live in the solution space of the super equation. Okay, so let's consider type 2b supergravity and on asymptotic ADS 5 times S5. And in this system, there are 5 conserved charges and 2 angular momentum, J1, J2, that give us the rotation in ADS 5, and 3 R charges, Q1, Q2, Q3, that give us rotation in S5. So given this setup, it's actually very natural to expect BPS black hole to show up at all these 5 charges. They have all these 5 charges independently. So if I consider the charge plane, in this case, it will be a 5-dimensional plane, and it's very natural to expect that at every point in this 5-dimensional plane, you can find some BPS black hole solution. But in reality, all non-BPS black hole solutions satisfy a mysterious charge constraint that take this form. So this equation gives us a 4-dimensional surface in that 5-dimensional space of these 5 charges. So all the BPS black hole solutions live on this 4-dimensional surface. So that's the solution space of the super equation. And now let's try to study the R-charge concentration and match with this equation. So we want to study the index. So first, the microstates of this BPS black hole, they are due to BPS states in angle spore superyamules, and we can construct this superconformal index. And in this case, I also add some favorable fugacity to refine the index. And this year, there's a very nice Frontier of Science award that is given to the work of evaluating this index in a larger limit. And so people have found this formula for the index. And it depends on the 4 fugacities, delta 1, delta 2, delta 3, and omega 1. So now let's try to use this index to derive where the BPS state should be concentrated at. So in this case, we consider, we identify R charge as 2 times the angular momentum J2 and consider this scaling region. And in this case, that exponent is 2. So both the angular momentum J1, J2 and the 3 R charges, Q1, Q2, Q3, scale like n squared and with some finite number. And so the previous superconformal index that sum over the entire space, the entire Hilbert space with all possible 5 charges. But now we want to consider the subspace with fixed J1 minus J2 and QA plus J2. So these two are the combination that commute with the supercharge. They are the analog of the J U1 symmetry in the two-flavor SYK model. So we want to consider the Surcombe index with these four charges fixed. And this index can be obtained from the previous one by applying an inverse Laplace transform. So, so here I consider trace with fixed four charges, and that's the index I want to study. And this inverse Laplace transform can be so that would be some integral transform of the previous formula, and that integral can be again evaluated by some saddle point approximation. And this saddle point approximation means that I want to extremize this formula. That's basically a Legendre transform. So the phase would be, I mean, this extremization. Sometimes people call that entropy, but it's actually entropy plus some imaginary number. The imaginary number is the phase. And now I want to, so I get the phase from this Surcombe index. I want to match that phase with the phase by the R charge concentration. And by matching that phase, we find this formula. So the imaginary part of this, that's a phase, should equal to the phase of this vector. So that's 2 pi times J2 at the concentrated value. Okay, good. So and that equation tells us tells us where the BPS state should be concentrated at. And this equation exactly reproduces exactly equal to the previous constraint in supergravity. Okay, very nice. So I think yeah. Yes. So so the thing people usually use is to move the left hand side to the right hand side. Yeah. So that's why, I mean, this constraint is exactly equal to the constraint that people find by saying that imaginary y is 0. Okay. That's right. Yes. For angles, for angles for super Young mules, we cannot quite check this formula because we only know the Fortuity states at very low rank. Okay. So I want to skip this part. So there are some relations between Fortuity and random matrix behavior, and also information entropy and entanglement entropy. But due to the time constraint, let me skip that part. So summary, we studied the supercharged cohomology in the angles 2 SYK model, and we've seen that the Fortuity states are concentrated at a single R charge in the cochain complex. And I also explained that R charge concentration is closely related to the genericity of the supercharge. And we also see that the R charge concentration in angles 4 super Young mule explains the charge constraint of the BPS black hole in ADS5. And so there are some open questions, open problems. So first, we know that besides this, the black hole that satisfy the R charge, sorry, the black hole that satisfy the charge constraints, recently there are some other black hole people have found. They are called the gray galaxy and the dual dress black hole. And I think it's important to understand this gray galaxy and dual dress black hole, the relation between them and the R charge concentration, because these solutions, they live away from that dimension 1 surface. And it seems that there's a tension between the existence of this solution and the R charge concentration. And another interesting thing is because Our conjecture is that this archive concentration it follows from the genericity of supercharge, and it's very naturally to study the case that you have a fully generic case. That's the n equals 2 random matrix theory, and that's also a very interesting direction. And another thing is that we would like to find more fortuitous states in more realistic models, like n equals 4 superYAG and D1, D5 CFT. And as so if we have more examples, then we can really test whether the fortuitous state in these models satisfy archive concentration. And finally, we can consider lots of generalizations. So the framework I introduced, the n equals 2 supersymmetry structure and also this quotient structure actually show up in many different theories. For example, in ABJM theory, ABJ theory, vector models, for the n equals 2 and n equals 1 theories, and also quiver or matrix quantum mechanics. So there are lots of things to explore. Okay. Thank you.
Yes.
So integrability usually only show up in the planar limit. And yes, I will expect they can only see monotone states. But for fortuitous, we say we actually really need to consider finite n. So the 1 over n perturbation theory cannot see fortuitous states.
Yeah, I mean, but even just to comment on that, I would have thought that even for the monotone states, since you're looking at states whose energies are order n squared, integrability would still be less constraining.
But for monotone state, you can fix energy and take infinite n limits.
But if you want to compare with the black hole spectrum, you want to sort of keep the energy of order n squared.
That's right, yeah.
But I wanted to ask about these gray galaxies. That I would have thought was some superposition of fortuitous states with monotone states. I would have thought that sort of the halo around which makes up the galaxies is like monotone. Now, is there a statement that one can make more generally that if you try to take linear superpositions in the Hilbert space of monotone and fortuitous states, what happens? Whether they stay fortuitous or do they stay monotone?
It's not taking a superposition of states. It's more like taking product of states.
I mean, from the black hole point of view, it would seem to me like it's more of a superposition.
It's superposition of classical solutions.
Yes.
But as quantum states, it's not superposition of quantum states. Yeah. Yeah. So more like product of two states. So from the cohomology, you can consider product of two cohomology, and to see like whether the resulting thing will give you non-trivial cohomology.
I see. And is that known in general or?
There's actually a very interesting study by Kim and his collaborator. So they consider they consider n equals 4 super-Young-Mills, and that's why they can only focus on smaller n. And they can take some fortuitous class multiplied with some monotone class, and the thing they see is that if the monotone class has relatively small R charges, and then the resulting class will actually be trivial. But for the monotone class, if that has large enough angular momentum or R charges, the resulting class can be non-trivial. And they take that as evidence for the square galaxy or dual dress black hole, even though that product computation is as smaller.
Thanks.
When you say add, you mean product or?
Yes, space, vector space.
Yes. Yes, that's right. It will be fortuitous. Oh, that's right. That's right. So in the definition, there are several points I I'm not that rigorous, but so the rigorous definition is that after you model monotone state, the remaining things are fortuitous. Yes, yes. If you consider full space and the monotone subspace is actually a very small subspace. And so after you margin out this very small subspace, you still get the majority of states. So in that case, let's see. But the black ADS2 black hole is still different from the just vacuum. And locally, they are related by coordinate transformation, but they are different solutions. I think globally you cannot do that. Only locally it is. That's right. So when I said this distinction between smooth horizonless and black hole, I really mean globally. Yeah.
Okay, if there are no more questions, let's thank Chi-Ming again.